We are welcoming our next speaker, Carlos Benavides-Riveros, and he will be talking about using quantum computer for our great physics challenging. So welcome, Carlos, the stage is yours.
Thank you very much for the introduction. I'm very happy for the opportunity to present the results here and also to meet Oxana after several years. So the work I'm going to present was done with this gentleman here, Lipen Chen, Sebastian Mantilla, who are in the same place that I am, in the Max Planck Institute in Dresden, Christian Schilling, who is in Munich at this moment, and Stefano Pitales in Modena in Italy. So the idea of this work is to propose a method to compute excitations using quantum computers. So we have in mind, in general, quantum excitations, so of quantum many-body systems, fermions, bosons, or even polarons or polaritons. But the results I'm going to present as an introduction to the method are in particular developed for fermions. So what is our goal? So the quantum eigensolver that we know from to use in hybrid systems has been developed mainly for ground states. And this is not a casualty. The ground states have the property that they can be computed using the Rayleigh-Ritz principle, variational principle of quantum mechanics. So if you minimize Hamiltonian, are likely that if you correctly minimize, you will be very close to the ground state. But this variational principle in this way doesn't exist for excited states. So excited states are more challenging. So our idea is to develop a method not only to compute ground excited states, but actually to compute all excited states for bound Hamiltonians. So our idea is to use quantum computing basically to diagonalize a Hamiltonian. So with this idea in mind, let me introduce why excited state processes are important. Maybe I don't have to insist much that they are very important, but sometimes for some communities, it is not so clear, especially because we push a lot of effort in computing ground states. So I'm going to give just 3 examples. Polaritonic chemistry, in which using light, you can modify the excited states processes. So for instance, if you couple a molecule with a cavity, then you can split or you can change, for instance, these points, which are the conical intersections. And then the adiabatic process or the non-adiabatic process will be changed. Also, for many variable localization, it's important to have the spectral analysis. So the behavior of the complete spectrum of a Hamiltonian, not only the low excited states, but actually the whole set of states. And then, given the difference of the energies between them, they can conclude if the system is localized or not localized. And finally, polaronic states are also important for photovoltaics. So of course, these potential energy surfaces play a very important role in photovoltaics. So in general, in practice, we are facing the following problem. We have a Hamiltonian here. This Hamiltonian, I call it, I split it into 2 parts. One is this small h. Small h, I mean the easy part of the Hamiltonian. And by easy part of the Hamiltonian, I meant basically the non-interacting part. So the kinetic energy or the external potential. This is non-trivial. I'm not saying that it's trivial, but sometimes it's easier because we don't have interactions. So we have free fermions, free bosons, etc. But as soon as you have this W, and by this W I mean the quartic term, the Hamiltonian, so interactions, the problem becomes very challenging. And this is the many-body problem of quantum mechanics. Because as soon as you have interaction, the problems could, then you have to really need an access to an exponentially large Hilbert space. But if you will go back to our classes of quantum mechanics, we are interested in the eigenfunction and eigenfunction and eigenvalues and eigenvectors of the Hamiltonian. So we are interested in a problem like this one. And usually these energies here, can be the generator or not. It is just a cartoon that these are above the ground state energies. Usually all these are bounded from below. In our case, I am also interested in Hamiltonians bounded from above. But what is true is that in general, you are going to face a spectrum like this one. So here is in terms of the coupling, lambda. So if lambda is 0, is the only part is h. So let's say the easy part. And if you increase the value of lambda, you are going to face, you are interested in a spectrum like this one. And this red line here is the ground state energy. And for this ground state energy, we have a plethora of methods. I'm going to mention just a few, but there are this list is totally incomplete. Density functional theory, density metric normalization group, reduced density metric functional theory, quantum Monte Carlo, tensor products, neural networks, density metrics embedding theory, variational ansatz, etc. These methods are also in somehow incomplete. So this method, some methods work for fermions, other methods work for bosons, other methods are very good in 1D, others are really good in 3D, but these methods are not universal in that sense. From the point of view of what is explanation that we have so many methods is, of course, I say, the Rayleigh-Ritz principles. If you minimize this in the set of the Hilbert space, in the whole Hilbert space, this sandwich here of the Hamiltonian, you are likely to obtain something very close to the ground state. And this is the reason that these methods are, or we have a lot of methods because they use the same principle. So from the point of view of quantum computers, variational quantum Eigensolver was developed to produce also ground states, but with a different philosophy. The philosophy here is, of course, the same one here, at least, that you can minimize in the set of the Hilbert space. But this, so you map the complete Hilbert space by a unitary transformation of some vacuum. By vacuum means here in practice, for fermions, for instance, some state. So you fix the number of particles and you have some state, which is your reference state. Usually you can think that this is the Hartree-Fock state. And then this guy here, this exponential high here is what is called the unitary coupled cluster. So you use basically the exponential of an anti-unitary operator, t minus theta. And this t can be expanded in this way. So here is basically what chemists call one particle excitation, two particle excitations, three particle excitations, etc. And all these, basically, these theta are the variational parameters. So the idea of the quantum Eigensolver that was proposed in 2014 by the group of Aranas Purugusic and all these people is basically that this state can be prepared in a quantum computer. And then the minimization is performed in a classical computer. So this is basically the seminal paper of what is called hybrid algorithms. That is not fully quantum, but has an important quantum part, which is the state preparation. Now, why this unitary coupled cluster ansatz is so important? So the idea, or the crucial thing to understand here is that this is very cool approach because it's a unitary transformation of a state. So we know that unitaries can be implemented in quantum computers. But the thing is this unitary coupled cluster ansatz is inefficient in classical computers. Even though we know that is a sort of called the standard to compute the ground state properties of chemical systems, this is inefficient in classical computers. And the reason is this: if you expand this sandwich here, so this unitary transformation of the Hamiltonian, you ended up with an infinite sum. So this doesn't truncate. And the problem with this lack of truncation is that instead of having a Hamiltonian with 2 terms or 4 terms, you ended with infinite Bohr interactions. So this is completely inefficient in a classical computer. However, since this is a unitary transformation, you can implement it at the level of hardware level. And then this is as we know, this is the workhorse operational quantum Eigensolver, and this is the promise of one of the near terms application of quantum computing for chemical systems. So to sum up here, this unitary coupled cluster, it's very well designed for the application of quantum computing for quantum chemistry applications. Now, going again to this problem, the variational Eigensolver that I showed before was designed mainly for the ground state problem. So I can ask you, maybe there is some interesting system here. So this is a state here, this 10th excited state. There can be some very nice properties. So I can couple with a cavity, reach that excited state, and perform chemistry in that state. But the question is how you can perform, or how you can find this state without doing, of course, exact diagonalization that in principle we assume that is impossible in real systems. So the state of the art in this moment is a very short summary of the state of the art of how to compute the state, excited states. So there are basically 2 ways. One is state average excited state calculation, is that you, instead of working with one state, you work with a superposition. So in this way, incoherent superposition of some states, 2, 3, 4, and then you do they are orthogonal, and then this trace here, if you minimize this trace, it will give you these few states. This is a way to compute excited state properties, and this is what is done in density functional theory. So this is a way that functional theories they use recently. As you see, these papers I'm going to the paper I'm going to cite are quite recent, and this is a way to access to these states. But there is another way, more let's say clean, is that state-specific excited state calculations. So how is this? Of course, you have the ground state that you find by minimization. You can perform a minimization in the orthogonal space to the ground state, and then you are going to find the first excited state. Then you can perform a minimization in the orthogonal space to these two states, and then you can find the second excited state, and so on. So this takes this form. You minimize this sandwich here, and some penalty terms in the projection of the new, in the minimization, on the states that you knew before. So, of course, this is very costly because you have to perform these several minimizations. And of course, you are going to obtain a degradation of the quality of the states that you're going to find, because you cannot ensure the total orthogonality. And as soon as you reach for the three states, the orthogonality with the real state will be very difficult to ensure. And this is what's done in variational quantum computers. This paper is 2020, and this paper also is 2018. This is not quantum computing, but this is neural networks. So machine learning can be also applied in this context. You see here, all these prescriptions are limited to few states. So our idea is basically maybe we can make a synthesis of unification of the two approaches to perform a minimization such that you really can compute all the states with some really good quality. And this is what I'm going to present a solution of this problem. So let me first introduce two inspiring ideas. One is could be esoteric for some people, but the people working in black hole, for instance, it's very common this. So thermo-fields. So the idea here is to duplicate the Hilbert space. So you start with a Hilbert space where you want to find, and then you perform a duplication. So you create a fictitious Hilbert space, which is coupled with the other one. So why so? So imagine that we are working in the thermal distribution. So this is the thermal state, and here's the thermal weights. And of course, you have a density matrix. So, and if I give you an operator, an observable A, the average of this is just the trace of this A in this density here. Now, the trick is this. You basically convert this bra in a ket. This ket belongs to the fictitious state, and this is what is called the thermal vacuum. As simple as it is. Now it's just, you can see that, okay, it's a very simple purification of this state. Of course, I have to pay a price in some moment because I am duplicating the Hilbert space. But so on at the end, I am working with only one pure state. And to recover the value of this observable is just the expected value with this pure state just here. And as I told you, this thermophile idea comes basically for the black hole community, and this is what people use to study entanglement between two black holes. And the striking idea for us, or the very cool idea, is that maybe you can think that this pure state is the ground state of some Hamiltonian. And actually, there are papers, those two papers, that they try to find this, actually to prepare in the lab, this thermal vacuum as the ground state of a Hamiltonian, not exactly the same Hamiltonian as before, a different Hamiltonian, but then it's very cool because then by a minimization in this duplicate state, a pure state purification, minimization, you can find this thermal state. So with this, we want to introduce W fields. W fields is exactly the same idea. So we make this average here with some orthogonal states, and we do the same trick here. The square root here with this, we turn this bra in a ket, and this belongs to the fictitious state here. And then again, if I want to find the energy, so instead of doing the trace, with the density, is the average with this pure state. So if more details are in this archive preparing version of this work. And now, so why we use this? Just to give an example. So this is a very simple example. Imagine you have the most simple Hamiltonian you can imagine is a free Hamiltonian. This is fermionics. In principle, here I don't specify it is for fermions or bosons. The statistics come later. But this Hamiltonian is very easy. It is already diagonalized. So if you want to find the spectrum, it's very easy. Spectrum is just basically the sum of this. Here is for fermions, 0,1, but if you don't receive this is for bosons. And this is the whole complete spectrum of this. So the idea is, if you have L sites or L modes, I will put a W, W1, W2 for each mode. So I weight each mode with some W. It's positive. Each W should be positive between 0 and 1. And then I construct my W vacuum or my W field in this way. So this is the tensor product of these states here. So the eigenstate of the Hamiltonian, tensor product, the fictitious state. So here you can imagine that it's a tilde, right? And then of course, trivially, you can again reproduce all this energy. And then you can extract the energies. This is the power of this approach. So very easy, I basically just have rewritten the problem in a different language, but there is no gain so far. So to gain to gain something, I have to go to interaction. But first, let me introduce this. I will introduce an idea coming from superconductivity, is that this vacuum, this W vacuum, I'm going to write it like a superconductive state. So maybe if you're not familiarized with superconductivity is the idea of Cooper pairing. So you pair electrons. In this case, I'm pairing bosons of electrons, but here is not a thermodynamical state. It's just a fictitious state. I pair a real mode with a fictitious mode here. And this pairing here, which resembles superconductivity, can give you exactly what is called the BCS state, Bardeen-Cooper-Schiffer state. And this is exactly the state people use. So Bardeen-Cooper-Schiffer is studied for the first theory of superconductivity in the 57. So, but the power of this idea is that this guy here, this vacuum or this BCS-like state, can be written again like a unitary transformation of now is the real vacuum of the system. So it's the unitary transformation of the real vacuum. Now it's real. There are no fermions in this state. And this guy takes this form. So it's not important to enter into the whole details of this guy here. But the point is this is completely general for fermions or bosons. The only difference is that this is the connection between the theta, this theta guy here, and W for fermions and for bosons, cosine and cosine hyperbolics. Now I'm going to continue only working with fermions. And now the second cool idea is that this state can be also prepared in a quantum computer. So recently, Sager and Mazziotti, they prepare a real Cooper BCS state, so in the sense that this is resembling the Cooper pairing in a quantum computer. So in a quantum device, you can also implement this. And finally, if I want to turn on the interaction, there is a simple result that the interacting states here are connected with the non-interacting states, but also unitary transformation. And this is not a surprise result, because of course, these guys here, interacting states here, expand the same Hilbert space that is expanded by the non-interacting states. And between them, there should be only a unitary or even better, an orthogonal transformation. Because I mean, if you are working with real estate, you have here orthogonal transformation. But these guys are connected in a very cool way. A unitary transformation connects the non-unitary, the free states with the interacting states. And this is all the proposal, because then for the whole W field of the interacting state, I just do a unitary operation of the BCS state that they introduced before, that is for free fields or for free without interaction. And then the final result is that I can write the complete weighted sum of the excited states, actually the whole eigenstates of the Hamiltonian, as this formula here, the unitary transformation here, the squeeze operator that I introduced before, and the real vacuum. And basically, that's all. Because then I can perform a minimization, a whole minimization in this duplicate state. I using just this convention. This is the vacuum of this unitary transformation, the Hamiltonian, yes. And all these are dependent of W, because I use this convention. All these are transformed by the squeeze operator of the BCS state. And you see what we like of this result, the form of this result is basically the same result of the same, morally, the same structure of the fundamental equation of the variational quantum Eigensolver. So basically, our hope is that we can basically use all quantum state ideas to perform a minimization in the whole set of eigenstates. And the main result is that basically, by doing a one single pure state or ground state minimization, you can reach not only the ground state, not only the few excited states, but all the eigenstates of a bounded Hamilton, or a finite number of sites. right? But this, so far, right, this is just formally exact, formally cool, I will say, but it's impractical. Impractical because, again, we are stuck in how to expand this calculus. So in practice, for the implementation, we again put this unitary transformation, T daga minus T, and then we go back to the unitary coupled cluster. We do the complete round, and then what we can implement really is the E minus T daga minus T again here, and this is the prescription that we can implement in a quantum computer. So now I'm going to present some numerical results. These numerical results were performed in a classical computer, but we will use something which is called the factorized form of the unitary coupled cluster, which is a specific form of the unitary coupled cluster for fermions that you can implement in a classical computer. So let me show how validate the approach. So here is the Fermi-Hubbard model for spinless fermions. So this is the hopping term. Maybe you are going to recognize the hopping term. So this is so here is, this is the cartoon. So you have different sides and 3 fermions in this case. T is the probability to jump from one side to the other. And here n m plus 1 is the interaction. I mean, since they are fermions, they cannot be in the same place. So it's the interaction with nearby electrons. And this Hamiltonian play a fundamental role in discovering something which is called disorder-free many-body localization. It was discovered in 19 by groups of from here, from the Max Planck Institute in Dresden, and from Caltech, the group of Gil Rafael. So this is a non-trivial model. There are no spin symmetries because we didn't want to study, I mean, at least for this paper, spin symmetries. We are going to do it later. And this is non-trivial because the dimension is actually L to the square, where L is the number of sides. So this is the results. We implement something which is called unitary coupled cluster single doubles. Single doubles is in the exponential form of the unitary. We only put singles and doubles. Of course, this is a restriction of the complete Hilbert space, and it's clear that we cannot reach the complete spectrum in this way. But this is a standard way to write coupled cluster in quantum chemistry. So this is for 5 sides and 2 and 3 electrons. And you see, basically, this is the spectrum. In red is the analytical spectrum, the numerical spectrum, and the points, the dots, are the numerical values. And you see that here, basically, there is, I mean, the coincidence is quite remarkable. Basically, here there is no error. You only need like a very good number of throttle steps. Of course, you have to write the complete set of singles and doubles, and then perform the minimization. For the minimization, we didn't in this paper. We of course we can do something very sophisticated like reinforced machine learning, etc. But here we only want to do a very simple minimization system, so very standard minimization algorithm, and this is the result we obtain. For larger system, for L sides, the system for weak interaction in this sector and this sector, also for 2 and 3 sides, electrons, 2 and 3 electrons here, or fermions. For weakly correlated, for small u, the agreement is quite remarkable. As soon as you go far, very far, the agreement is not so great. But we think also this can be improved either by going to triples or by doing a different approximation to the triples. So there are some ways to extend this. So we think we can do it in the future, and also to improve the minimization algorithm. Because the difference between the number of sites with 5 or 8 is that the number of variational parameters increase basically exponentially. So we think that with machine learning, we can also improve these values. However, you see that the deterioration of the quality is for high excited states still. And then if you compute the neutral gaps, also the results are quite good. So here is for L equal to 5 and for L equal to 8. Of course, there is also the deterioration of the quality here in the sector, but in general, we believe that it indicates that the extension of variational quantum eigensolver to eigenstates, it could be quite straightforward. So this is like our first attempt to prove or to show that this method can work. Our next steps is to really implement it in a quantum hardware in the IBM computer, or to improve this approximation. So our conclusions are basically very simple. So it's what we propose is to go, instead of optimization of an ensemble of system, a pure statement duplicate Hilbert space, and using unitary coupled cluster approach, which open the doors to apply this to quantum computers. And our outlook is to to extend this for bosons, and bosons quite interesting because unitary coupled cluster doesn't exist as far as I know for bosons, and for polaritons, it could be possible to write a unitary coupled cluster. And then, as I told you, we want to introduce it to use really a quantum algorithm IBM or another hardware. And with this, I would like to acknowledge, of course, the funding, which is very important, the Max Planck Society, European Commission, and this consciences from Colombia. I am originally from Colombia, and Banco Santander from Spain. All these agencies have funded my research in the last years. So thank you very much for your attention.
Many thanks, Carlos, for this extremely well done presentation. And we already have questions that I'm going to read straight ahead. So again, thanks from Akash for a very nice presentation and a very general question, whether you could please comment how your approach will perform using current hardware friendly, such as hardware efficient ansatz.
Okay. So hardcore friendly, this is the question, right?
Hardware friendly.
Okay.
Ansatz.
Okay. So actually I have several ideas. So first, let's say that when we start this, we say, okay, we have the intuition that this is that can be implemented in a quantum computer, but you started last year and we didn't know. But it can be implemented very straightforward actually by this paper. So once we implement this step in a quantum computer, then the implementation of the unitary coupled cluster ansatz is also straightforward. And it's straightforward because this is what is really good study in the last 8 years. So if you put unitary coupled cluster in Google, it's very difficult to find something before 2014 for the reason I told you, because in classical computers it's basically impossible to implement it. But if you put what is done for unitary coupled cluster in the last 4 or 5 years, there is tons of literature. So basically, there is a lot of things that are known. Of course, there are some things that are known, but the way to implement unitary coupled cluster, at least for spinless fermions that we are totally sure that can be possible, it is, I will say, straightforward. So it's very easy. Just in the review papers of Aranas Purugusic, you can find basically the recipe to do it.
Very nice. Thanks a lot. The next question is quite close regarding friendliness, and how does the method scale with the requirements of the NISQ device? Okay, so in this case, I think we are just going behind, or we would like to use really at this point ground state methods. Of course, here we are limited. So for instance, if we go to IBM computers, we can do it only for 4 or 5 qubits, because if you have 4 or 5 qubits, real sites, we need to duplicate it, so we need 10. So of course, it is a price to pay, but it's not a very big price, because it's just a duplication of the number of sites. So I will say that this could be really possible to implement it. Actually, we are doing some progress in how to implement it. So the difficult part is actually not the quantum implementation. The difficult part is the minimization. But for the minimization, because what really scales with the number of sites is the number of variational parameters, and it goes really fast. So for instance, in the case of five sites, it's something like 15 parameters. But in the case of 8 sites, it's like 80 parameters. Then we are going to use machine learning. So the complete picture to implement this should be what people call it quantum machine learning. Very good. Thanks, Carlos. And your presentation provokes a lot of vibes and comments. Please follow them at the moment. They are on the chat in the Zoom. And if not all will be processed, just please go to Discord, and there is a channel dedicated to you. I think there are great questions, including a very social one, like how to bring more quantum technologies to Latin America. Okay. And so please join the people on the chat. I will do it. Thanks a lot, Carlos. And I please ask you to answer your screen and greet everybody in your native language. Okay, so I come from Colombia, so I'm going to do it in Spanish. Muchas gracias por la oportunidad de presentar mis resultados, y estoy muy contento de que la audiencia sea tan internacional. Si alguien entiende el español, gracias por acompañar la comunidad hispanohablante.
Goodbye.
Muchas gracias. Muchas gracias.